Assalamualaikum and good day everyone. Today we will be presenting our assignment entitled Investigation on High Temperature Low Sag HTLS Conductors. This presentation discusses the challenges faced by modern transmission networks, the role of HTLS conductors in overcoming these challenges, different types of HTLS conductors available in the industry, and their comparison with conventional ACSR conductors. We will also discuss practical application, empiricity calculations, and the overall benefits and limitation of HTLS technology. Before we begin, here is the outline of our presentation. First, we will explain the transmission network problems that have led to the development of HTLS conductors. Next, we will introduce HTLS conductors and discuss the recommended types used in the industry, namely ACCC, ACCR, and ACSS. We will then compare these conductors with the conventional ACSR conductor in terms of thermal limits, material construction, properties, and cost. After that, we will present two examples of HTLS implementation projects. Finally, we will discuss the heat balance equation, empiricity calculations under different environmental conditions, the effect of a wide angle, and conclude with the advantages and drawbacks of HTLS conductors. Why HTLS conductors? The demand for electricity is continuously increasing due to rapid industrial growth, urbanization, and economic development. As electricity demand grows, transmission lines are required to carry higher power levels. However, constructing new transmission lines is becoming increasingly difficult because of right-of-way or road limitations. These include land acquisition challenges, environmental restrictions, and high construction costs, especially in densely populated areas. Traditionally, utilities use ACSR conductors, which stand for Aluminium Conductor Steel Reinforced. Although ACSR conductors are widely used, they have several limitations. Their operating temperature is typically limited to around 75 degrees Celsius, and when temperature increases, the conductor experiences greater sag. Excessive sag can reduce ground clearance and compromise system safety. To overcome this issue, HTLS conductors have been introduced. HTLS conductors can operate at temperature between 150 and 250 degrees Celsius while maintaining low sag characteristics. As a result, they can carry approximately 2 to 3 times more current than conventional conductors without requiring tower replacement. What is HTLS? HTLS stands for High Temperature Low Sag Conductor. It is an advanced overhead transmission conductor designed to operate safely at much higher temperatures than conventional conductors while minimizing thermal expansion and sag. The key characteristics of HTLS conductors include: first, higher operating temperatures, allowing more current to flow through the conductor. Second, higher ampacity, which increases power transmission capability. Third, lower thermal expansion, resulting in reduced sag even under heavy loading conditions. Fourth, improved mechanical strength and reliability. Because of these advantages, HTLS conductors are commonly used for conductoring existing transmission lines, enabling utilities to increase transmission capacity without constructing new infrastructure. The first HTLS conductor we will discuss is ACCC, which stands for Aluminium Conductor Composite Core. Unlike conventional ACSR conductors that use a steel core, ACCC uses a carbon and glass fiber composite core. The composite core is significantly lighter and stronger than steel. Its design allows more aluminum strands to be used, resulting in lower electrical resistance and higher conductivity. The maximum operating temperature of ACCC conductors is approximately 180 degrees Celsius. Some key advantages of ACCC include very low sag characteristic, higher current carrying capability, improved energy efficiency due to lower losses, and reduced tower loading because of its lighter weight. Therefore, ACCC conductors are widely used in transmission operating projects where high capacity and low sag are required. The second HTLS conductor is ACCR, which stands for Aluminum Conductor Composite Reinforced. ACCR consists of aluminum zirconium alloy strands surrounding a composite core. The use of aluminum zirconium alloy improves the conductor's thermal stability and allows operation at very high temperature. ACCR conductors can operate at temperatures up to approximately 210 degrees Celsius. Some important advantages include excellent mechanical strength, high thermal resistance, good corrosion resistance, ability to carry very high current levels. Because of these characteristics, SCCR conductors are suitable for transmission system requiring maximum ampacity and long-term reliability. However, one drawback is that SCCR conductors are generally more expensive than other HTLS options. The third HTLS conductor is ACSS, which stands for Aluminum Conductor Steel Supported. Its construction is similar to ACSR, but it uses fully annealed aluminum strands combined with a steel core. The steel core carries most of the mechanical load, while the aluminum strands mainly conduct electricity. ACSS conductors can operate continuously at a temperature of approximately 200 degrees Celsius. The main advantages of ACSS are high operating temperature than ACSR, increased ampacity, relatively lower cost compared to ACCC and ACCR, easier installation because it is similar to commercial conductors. For this reason, ACSS is often considered a practical and cost-effective solution for upgrading existing transmission lines. This table summarizes the key difference between conventional ACSR conductors and HTLS conductors. Firstly, in terms of operating temperature, ACSR is typically limited to around 75 degrees Celsius, whereas HTLS conductors can operate between 180 and 210 degrees Celsius. Secondly, HTLS conductors have significantly higher ampacity, allowing them to carry much more current. Thirdly, HTLS conductors exhibit lower sag due to their advanced core materials and lower thermal expansion coefficients. In terms of construction, ACSR uses a steel core, while HTLS conductor may use composite cores or specially designed steel-supported structures. Regarding cost, ACSR remains the least expensive option. However, HTLS conductors provide greater transmission capacity and better long-term performance. Although the initial investment for HTLS conductors is higher, they can eliminate the need for new transmission corridors and tower upgrades, making them economically attractive in the long run. Therefore, HTLS conductors offer a practical solution for increasing transmission capacity while utilizing existing infrastructure efficiently. Thank you. I will now pass the presentation to the next presenter to discuss HTLS implementation project and heat balance equation.
Let's look at the first example from India. Due to the rapid growth in electricity demand, many transmission corridors become congested and could no longer accommodate additional power transfer. Building new transmission lines was challenging because of threat of fee limitations and high costs. To address this issue, Power Grid Corporation of India implemented reconductoring using HTLS conductors such as ACCC and ACSS. By replacing conventional conductors while keeping the existing towers, the transmission capacity was significantly increased. The main benefits were increased power transfer capability, no need for tower placement, and lower implementation costs compared to constructing a new transmission line. The second example is from United States, where the Western Area Power Administration installed ACCR conductors in its transmission network. The main objective of the project was to increase power transfer capability without major modifications to the existing infrastructure. Since ACCR conductors can operate at higher temperatures and carry more current, they provide a practical solution for upgrading transmission capacity. As a result, the project achieved higher ampacity, reduced conductor sag, and improved system reliability. Similar HTLS projects have also been implemented in countries such as Brazil and Thailand. To determine the ampacity of an overhead conductor, we use the heat balance equation shown on the slide. A conductor reaches thermal equilibrium when the total heat gain is equal to the total heat loss. In this equation, I squared R represents joule heating generated by the current flowing through the conductor. Qs represents solar heat gain from sunlight, while Qc and Qr represent convective cooling and radiative cooling respectively. This heat balance concept is based on the IEEE 738 standard and is widely used for calculating the maximum current carrying capability of overhead conductors. There are four important mechanisms involved in the heat balance process. The first is joule heating, which is the heat generated due to the conductor resistance when current flows through it. The second is solar heating, where the conductor absorbs energy from sunlight and its temperature increases. The third is convective cooling, which occurs when wine removes heat from the conductor surface. Finally, radiative cooling is the heat released from the conductor to the surrounding atmosphere through thermal radiation. Together, these mechanisms determine the operating temperature and ampacity of the conductor. Using the heat balance equation, we can calculate the ampacity, which is the maximum current that the conductor can safely carry. As shown in the equation, ampacity depends on several factors including wind speed, wind angle, ambient temperature, solar radiation, and conductor surface properties such as emissivity. Generally, higher wind speed improves cooling and increases ampacity. On the other hand, higher ambient temperature and solar radiation tend to reduce the ampacity. Therefore, environmental conditions play an important role in determining the current carrying capability of overhead conductors.
These are the parameters we use for the ampacity calculation, which is ACCCW, ACSR rate, and environmental. The ampacity is calculated using the heat balance equation by calculating the solar gain Qs, convection QC, and radiation QR. This equation balances the heat generated by the conductor with the heat loss through the convection and radiation. The maximum current is obtained when thermal equilibrium is achieved. This table shows the ampacity results for the ACSR rate and ACCCW at different wind speeds. As wind speed increases, the conductor can carry more current due to better cooling. This graph shows the ampacity increase with wind speed. Higher wind speed improves the convective cooling, which reduces the conductor temperature. ACCCW consistently has higher ampacity than the ACSR rate. Besides wind speed, wind angle also affects the ampacity. In this analysis, wind angle values of 0.1, 0.5, and 1 are used at constant wind speed, which is 3 meter per second. This graph shows the ampacity increase as the wind angle factor increase. The highest ampacity occurs at wind angle equals at 1 where the wind is perpendicular to the conductor. ACCCW again demonstrates better performance than the ACSR rate. From the results, wind speed and wind angle has a significant effect on the ampacity. HTLS conductors such as ACCCW can carry more current because they operate at higher temperatures and have lower sag compared to the conventional ACSR conductors.
So next, for the advantages and drawbacks of HTLS conductors. For the advantages, the first one is higher ampacity, which is 2 to 3 times higher than ACSR. Lower conductor sag at elevated temperatures, can operate at temperatures up to 180 to 250 Celsius. Existing towers can be reused, which is no major infrastructure upgrade. Improve transmission capacity and grid reliability.
For the drawbacks, higher initial investment costs, required specialized fitting and accessories, installation and maintenance require trained personnel, limited availability compared to conventional ACSR, and the last one is economic benefit may not justify use for low loading lines. Finally, for the conclusion, HTLS conductors solve transmission congestion problems. SCCC, SCCR, and ACSS provide significantly higher ampacity than ACSR. Wind speed and wind angle strongly influence conductor ampacity. HTLS conductors can increase power transfer without building new transmission lines. And the last one is although initial cost is higher, long-term benefit outweigh conventional SCSR. And these are the main references that we referred to throughout this presentation.